Alright, welcome back guys. So this is probably the last video we're going to go over for this lesson 4.2, 4.3. Just to continue with the multiplication rule probability, we are going to go over the next example, so where the multiplication rule become a little more useful rather than just choose just from a procedure that consider that involve two selection. In this case here, we have more than one selections, and then we have this thing called the 5% guideline for cumbersome calculation is being applied here. So this saying that when calculations with sampling are very cumbersome and the sample size is no more than 5% of the size of the population, treat the selection being independent even if they were actually dependent. So this is where we have larger selections and the selections are dependent, but because the calculation is cumbersome, is tedious, we're gonna treat the selection as independent because the sample size is no more than 5% compared to a larger population. The value of the probability doesn't change quite significant, so we can go ahead and treat it as independent to make the calculation more convenient and more applicable than just and I'm going to show you guys that in this example 3 here. So this say that in a airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 10,000 scales at a local airport and found that 1,259 were defective scales. If 5 scales are randomly selected from this larger population without replacement, find the probability that all 5 are defective. This is using the probability of a local airport from a relative frequency and then apply for larger populations. So we don't know if, well, we probably know the larger population is going to be more than the 10,000 here, and the 5 scale, which is a sample size, so n being 5 here, that's going to be very small compared to a larger population. So this is just a local airport only have 10,000 scale. So larger population would consist of 100,000 scales, right? So the sample size, we're looking at the selection just 5 scales here, 5 scales being selected, randomly selected. So that's going to be much less than the 5% that we referred to up here. All right, so let's go back to see what the problem is asking here. If 5 scales are randomly selected from this larger population without replacement, so that means the selections are dependent. Find the probability that all 5 are defective. So selections are selected, and we say selections without replacement. So that means the events are dependent. So that means dependent. Okay. So we're looking at the probability of all 5 scales are defective. Okay. That means what is the probability of the first one is defective and second one defective and fifth one is defective. I can't spell defective here. Defective. Okay, so this is where we apply the multiplication rule, right? So if we were to apply the multiplication rule, the general multiplication rule, because the selections are dependent, it would be P of first one is P of first one times P of second one, given the first one is defective, times the probability of the third one, given the the first and the second one are defective. So it's a lot of work here, right? So to sum this up, this is what it looked like. Okay, all right. It looks like this. Let's see. The first one we have 1259. Okay, over 10,000. Okay. And the second one will be 1258 over 9,999 because selections are without replacement. If the first scale being selected is defective, we put it away. We don't put it back to the population. So both numerator and denominator decrease by 1. So 1257, 9998, 1256, 9997, 1255, 9996, right? So imagine type of all these numbers here. So if we were to do this, calculator is just a pain in the butt to do this here. But let's just go ahead and do it. 1259 times 1258 times 1257 times 1256 times 1255, and then we're going to divide that by, so I'm going to go ahead and store this answer to A. So we're going to divide that by 10,000 times 999 times 9998 times 9997 times 9996. And then we're going to go ahead and take the numerator, divide by the answer we just got there. So that's going to give us a very small number. So what I got here is 3.14 times 10 to the negative 5. So that's 3.14 times 10 to the negative 5. Really small probability. Okay. Now let's go ahead and apply. The 5% guidelines. 5% guideline for cumbersome calculation. So let's go ahead and do that. That means these selections are treated as independent. If they're independent, we just take the multiplication of these numbers 5 times. So we're going to say the probability of the first one being defective will be 1259 over 10,000 times the probability of the second one defective is 59 over 10,000. And then we're going to keep doing this for 5 times because there's 5 scales being selected. 1259 over 10,000 times 1259 over 10,000. Right? So it is the same thing, taking this number and raise it to the 5th time. The 5th powers, sorry. So 1259 divided by 10,000. And then raise that to the 5th time. Now check this out. The answer we get from this treating the independent events is 3.16 times 10 to negative 5 powers. So not so much difference there, right? But doing this way, it saves so much time with the calculation, the computation of getting the answer. Imagine our selection is not 5 scales, but 100 scales are selected from an even larger population. Certainly we don't want to do this first method here. That's just too much work. Okay, so that's when we know the 5% is being applied. And then how do we know, how do we calculate the 5%? Well, 5% of 10,000, 5% of 10,000 is I think 50 of 500. So the scales we're picking is only 5 scales, so that's much lower than the 5%. Okay, so that's the example where we use the multiplication rule, where we to treat the dependent events as independent events. Next example 4. What is the probability of getting at least one heads in a 2 coin toss? So in this case here we have 2 coin toss, or 2 separate coin toss, or more than one single trial. This is when we know that we apply the multiplication rule, but it also have at least one. That's the terminology that we're going to use in this case. And let's look at how we're going to do this. So let's go ahead and define A be the event that getting at least one head in 2 coin toss. Okay, so I'm gonna go ahead and just leave this A bar for now, and then we're gonna come back to that. So what does it mean to get at least one heads in 2 coin toss? That means the probability of event A can be getting at least one, meaning one or more one or more heads out of 2. That means probability of getting, let's call that x. X equal to 1 is 1 heads, or the probability of x equal to 2, which is 2 heads. So you can get 1 heads or more, meaning you can toss 2 coin, you can get 1 heads out of 2, or you can get 2 heads out of 2. So this is what we're looking at here. And from there, we need the sample space to figure out these probabilities. So we can say the sample space of tossing 2 coins would be either get 2 heads, head tails, tail heads, or tail tails. So it's out 4 possible outcomes. So how many different ways we can get 1 head? So that'd be, let's see, that'd be 2 out of 4 plus exactly 2 heads. That's 1 out of 4. So 3/4 is the answer. So this is one way of doing it. So this way here requires to know the entire sample space to figure out these probability for these events. Now, if we use the rule of the complement rule for probability, this is what we're going to do. We're going to say, let A be this event, then let's define the complement event of A. So what would be the opposite of getting at least 1 heads out of 2 coin toss? Well, that means getting less than 1 head, so less than 1 heads out of 2 toss. Well, what does that mean, getting less than 1 heads? That means it's 0 heads. Getting 0, that means getting 0 head out of 2. That means getting both tails, right? Okay. Well, if we do that and apply the complement rule, so use the complement rule of probability. Okay, that's saying that any event A, P of A plus P of A bar is going to equal to 1. So that means if we try and figure out what P of A is, we can subtract P of A bar from the other side from 1, and then we can get the answer. So in this problem here, what we can do is we can say the probability of getting at least 1 head out of 2 coin tosses can be equal to 1 minus the probability of getting no heads at all out of 2 tosses, which is both tails. That means 1/2 times 1/2, which is 1/4. That gives us 3/4. Okay. So either way will work. The complement rule of probability is more useful if we're looking at a larger selection, like in this next one here when we do 6 boys here, or in this case selection is 6 different births. I will say this 2 example on Zoom in case you want to ask me to go over it. I will record it and post on Canvas, but I'm gonna go ahead and stop on this note here, allow you to do some homework and come back with questions